Okay, let's start again. From the previous, the voltage, the cascading of the voltage amplifiers, I forgot to mention that if you look at that formula that had the formula had Z input at the top and Z output, Z in. It's clear that if we were dealing with ideal voltage amplifiers, we would have to require an ideal voltage amplifier should have Z input infinite for an ideal V amplifier. We need Z input infinite and Z output 0. Z input infinite means that it doesn't draw any current, isn't it? Because the current in input, we've removed it now, is the V input over Z input. So if Z input is infinite, there is no current going in input, which is good. So it only requires voltage, effectively, no current. And the output impedance should be 0, because in this way, there is no voltage divider, as we saw previously, happening. So what you get out is always the same value of the amplification that you would expect for any value of the load. There is no voltage divider involved. So this is what we would expect for an ideal voltage amplifier. And if you go back to the formula we saw previously, and we assume that all the stages are indeed ideal, that fulfill this requirement, you see that the term in the product was Z in I over Z OI plus Z in I plus 1. So if this is infinite, this is 0, and this is infinite, it makes 1. And so the total amplification is exactly the product of all the ideal, amplifications of each stage, the AV infinite values. I don't know if you, unfortunately, I should have done it later previously when I had the formula here. Okay, but the point is, if you are in this situation, which basically means that it's an ideal amplifier, then these terms become 1. And so the total amplification of the cascade is indeed the product of the amplification of each stage. If not, the total amplification is smaller, as we discussed previously, because there are also these terms to take into account. And probably I can repeat this concept here. So if we are talking now of current amplifiers, the ideal current amplifier should have input impedance 0, because you don't want to oppose any resistance to the current flowing into the circuit. That's why in input the impedance has to be 0. In output, though, this should be infinite. Remember, Z output is in this configuration for a current amplifier. Obviously, when some current is flowing there, a little bit is flowing here as 2. So you understand that this requirement means here I don't want any current to flow internally. I'm wasting current. That's the point. So these are the ideal requirements for a current amplifier. And so now let's go to the current amplifier, cascading current amplifiers. So there is no point in going through the entire story again. I've repeated what we said previously for the cascading of the voltage amplifiers, now for current amplifiers. So n stages, same story. The only thing here that changes is that, as compared to the voltage amplifier, is that now here we have a current divider. And here, as you can see, I'm calculating the current at this point. The current basically goes to the input of the second stage, is calculated in this way. You see, this is the current divider. So it's the impedance of this branch divided by the sum of these two branches. This is to calculate the current in here. This is the rule connected with the current divider. And so we realize that when this stage is connected to the others, the actual amplification of the stage, which is the current at this point divided the current at this point, which is calculated here, is not just AI0 of the stage one, but is actually multiplied by this factor. So same story as previous, and so previously. So we can calculate the amplification of the entire stage in similar ways as we did previously. So this is the formula, and again we have this last term in case you attach it to load RL. And we can try to think again, if these were all ideal, how would this be transformed? Well, Z0, Z output must be infinite, so all this must be infinite. This is 0, this is infinite, overall this is 1. And so again, if we were in ideal, and only in ideal situations, we would have that the total current amplification is this. If not, will be smaller, because we need to consider those. So I hope that I've made you realize the power of this, and also the power of what we've just done last week with the learning about creating these relatively simple amplifiers. But you can see now what could be the potential, what you can achieve just learning one single amplifier. You can do all then these other things to increase the amplification, to change the impedance, and to all possible things. And just to conclude, in general, just to conclude this matter of creating amplifiers. So here we've seen now how we cascade them, identical amplifiers, or say a series of amplifiers, to increase, I don't know, the amplification, either in voltage or in current. But in general, the architecture could be, the architecture of a complete amplifier could be broken up, at least I would say, in 3 pieces, 3 main blocks. So this is what we've seen now, the amplifiers. Cascaded, whatever. The first stage, this is V input or I input. The first stage is the input stage, which is actually used to achieve the desired input impedance of the overall cascade. As I said, if you wanted this to behave as a voltage amplifier, the input, you would want it to be something that has a Z input very, very large, eventually infinite, because you want all this to behave overall as a good voltage amplifier. And we said previously, a voltage amplifier ideally should have Z input infinite, Z output 0. And so that's why the input stage is required. is required to adapt the input impedance of the entire circuit. And you realize maybe probably now what I'm going to say here. So the output stage is required to adapt the output impedance. If it was a voltage amplifier, you would want Z output to be 0 or close to 0. If it was a current amplifier, to be infinite. So the output stage will adapt the output impedance of the circuit to the need, whether if it is a voltage amplifier or a current amplifier. Operational amplifiers, for example, are generally voltage amplifiers, so they have an input stage with extremely large, near infinite input impedance and very, very small output impedance. So at this point, I was going to briefly mention some additional circuits. I want to do it on the board. I will actually use the screen. Well, I was planning to do it on the board, but because I want to show you also some other stuff, I will actually do also this part on the screen. So we've discussed cascading voltage and current amplifiers. So I wanted just to briefly, mention this again. As I said, you will find all these if you are curious in these notes I'll give you. So how can we now cascade amplifiers? We've seen the common emitter. What if you wanted to cascade them? So the easiest thing to do is to use the C-coupling method. C-coupling means we've studied this. For example, imagine this was the one of the CE3 voltage divider configuration. So we know everything about it, all the 4 parameters that I've also written there. So let's say now that I'm not happy with its, voltage amplification. I've made the design, I've calculated the resistors and everything, but it's not enough. We cascade it. The way to cascade it is simply to, and this is what C-coupling is about. Imagine here, as you can see on the screen, you have a sequence of the same, exactly the same resistors, they are all identical, a sequence of N of these circuits, and the connection between the output of one and the input of the other is through a capacitor. The capacitor is important because it decouples the DC component. So each stage is effectively independent from the other. That's the nice part of C-coupling. Each stage you've studied it on its own, you've defined it, and then you take it and you copy and paste it. And put between each stage and the other a capacitor, and you get the cascade of them. Obviously, the cascade of these N amplifiers will obey the concepts we've just gone through generally when we cascade amplifiers. So, for example, for this example here, you should expect the total amplification will have, again, this behavior here. That's the formula we saw previously. Or if it was, if you were using this cascade to do a current amplifier, you would use this thing here. Remember, you need to choose the capacitors in such a way that for the frequency you are interested, these capacitors are effectively have an impedance that is effectively zero. What zero means, I've discussed it last week in the post-lecture video. You know, it's important what you choose, what value you choose for these capacitors, because they will have an impact on the overall frequency response of the total amplifier, you know, the bandwidth, as we saw last week in the post-lecture video. Okay, so this was the simplest way of approaching cascading for us. A bit more complex is actually DC coupling. So I take, you know, different amplifiers, could be, you know, the common emitter with the common base or a common collector and so on and so forth, and connect them, but now without using capacitors. I just said that capacitors is nice, C coupling is nice because it's simple, but introduces a lot of capacitors. And capacitors have an effect on overall the bandwidth of this total amplifier, let's say. So really, you don't want to use capacitors. If you are, you know, an analog designer, let's say, if you're creating a nice amplifier, you really want to avoid using amplifiers, using capacitors. So that's why DC coupling is important, trying to remove as much as possible capacitors from the circuit. Obviously, removing capacitor means that each stage will now interact with the other one. This is an example of an amplifier, DC coupled. As you can see, this is our standard common emitter voltage divider configuration, but it's coupled with the second stage that is a common collector. And they are coupled in DC mode as well. Okay, so here, when you go and do the DC analysis of this circuit, you need to analyze the entire circuit. You can't go stage by stage. So that's the additional complexity in this. But the advantage is there is no capacitor in this link. I'm removing a capacitor from the way. Okay, so and you will see. I will show you in a moment later in the circuit diagram of operational amplifiers. There are effectively one or two capacitors. They are all DC coupled. So interesting things now still under the umbrella of cascading things. There is this very nice application that is called the Darlington Pair. This is really a clever idea of putting together two, in this case, NPN transistors in this way. So you can see that the collector current in the stage one is effectively fed into the base of the second stage. If we remember that between the base current and the collector current, there is an amplification factor that we called beta in DC mode, or HFE in AC mode, both of the order of 100. If this was the IB, and let's say that IB is entering here the first stage, the current in the collector and in the emitter of stage one will be 100 times bigger than IB that was coming in this side. But then this 100 times bigger current is effectively the IB to the second stage. So the collector current to the second stage is now 10,000 times bigger than the initial IB. So we realize already from this very simple qualitative approach, discussion, that this configuration, the Darlington configuration, the Darlington pair, behaves effectively as a new BJT that has a beta that is the product of the two beta. So very, very high amplification, current amplification. And so I'm not going into further details. I've done here the whole analysis just to prove what I just said, that the Darlington pair, and this is summarized here, the Darlington pair effectively in DC is equivalent to this, a BJT, where IC is beta D. Beta D is the beta of the Darlington pair. So these are, you see, exactly the same formulas that we have gone through for the standard BJT. So it's quite nice that it behaves exactly like a BJT, a normal BJT. But simply beta D, which is the beta of this Darlington pair, is effectively the product of the betas of the two transistors that are involved in the pair. This was in DC. In AC, if you do the analysis, you can demonstrate the same, something similar, and I did it here. There you go. So if you take the Darlington pair and you do the AC analysis using the hybrid model, you realize that indeed it can be written as equivalent to this model, which is exactly the hybrid model we've seen, the same form, the same shape. Simply, again, the relation between IC and IB has a similar form to the hybrid model we've seen for the standard BJT. Simply here now we have HFED for the Darlington pair, similar for IE, similar formula that we already know, and simply HFED is effectively the product of the two amplifications of the AC small signal amplification of the two stages, and similarly HIED is also the product of the two input impedances. Oh, this is quite nice now, this realization from this result. What I see is that the Darlington pair not only has a huge amplification, current amplification, both in AC and in DC, but also what I see here is that the Darlington pair has a very large what? HID is the input impedance of the model, and HI1, so HI2 time HFE1, remember HFE is 100, for example, HIE is 1 kilo. This means that the HIE, the input impedance of the Darlington pair in AC regime, is actually 100 kilo ohm. So the Darlington pair has huge current amplification and very large input impedance. So we like it a lot for voltage amplifiers, very large input impedance. Here is an application, an example of using the Darlington pair because we realized the Darlington pair effectively is a BJT, operates like a BJT, simply larger everything, amplification, input impedance. So I could go use it with all the amplifiers we've seen up to now, replace the BJT with a Darlington pair. And you will get, obviously, a much stronger amplification. The only thing to keep in mind when you use the Darlington pair, I did it probably up here, yes, is that because you have two BJTs connected together, you see the two BJTs here, so for both have to be on, active. So if I need to turn on this one and this one as well, I need to have VB on here, VB on there, and they are in series. So this means that in order to turn on the pair, I need to have not 0.7 volts applied to VB, but I need to have twice as that. So that's the only point of, that someone needs to keep in mind if you wanted to use a Darlington pair. And so this is this example. Another thing, another nice, or maybe a connection that you may have seen or you may come across in the future, and I'm just telling you how it's called, is this Cascode Connection, where you see the emitter just for your curiosity to know the names and how they look like, these connections. And you see, the first stage is effectively connected as a common base. You see the base is connected to ground. And the second stage is a common collector. You see here, the collector is connected effectively to a common potential. Each one of these type of connections that I'm showing you have some peculiarity. Okay, this, for example, has very high gain also, both in voltage and in current. So there are reasons why people obviously may choose one or the other. Another example of cascade connection between two BJTs. This is very similar to Darlington. The only difference is that this is NPN, the second stage. This is PNP. Overall, it behaves like the Darlington. Simply, this combination behaves effectively as a very powerful PNP transistor. So the only difference from the Darlington is that the Darlington would behave as an NPN, if you were using NPN transistor. This combination here would behave in the end as a PNP. Okay, so that kind of completes what I wanted to show you in terms of cascading amplifiers, and also what are some nice configurations like the Darlington, for example. I think that's quite nice. Let me show you, just to stay on this cascading subject, let me show you one of the most probably popular operational amplifiers ever built. So this is the LM741. I remember using it when I was in high school or at the university. Probably you've used it as well. And the reason I'm showing you this is because not only of nostalgia, but because I wanted to show you the circuit diagram. So, nothing to be scared about. And you know why I'm not scared? I go back to my initial statement. So we started with linear circuits, resistor, capacitors, inductor. We talked about semiconductors. We understood the semiconductors. We have been able to understand the PN junction. And using the PN junction, we understood the BJT. And now that we know the BJT, well, let me say we know the operational amplifier. It's all BJTs. It's a lot, I agree. And also, since we spoke about, we talked about previously the different ways of connecting things, or cascading maybe things, how many capacitors do you see in there? Is the only one. So this is all DC coupled. You can see that in this kind of applications, people don't want to use capacitors in cascading things, because, as I said, this will have bad effects on the overall bandwidth of the circuit. Actually, the operational amplifier amplifies also in DC. And this is the reason why people don't want to put capacitors in. That's why this is all DC coupled. Now, I challenge you to find something you know in that circuit. Some of the things we've talked about. Let's see who finds it first. There are a couple of things you can identify. Yeah? Yes, correct. Resist. Sorry? Let me make the question more specific. Configurations of BJT amplifiers we've talked about. Can you identify anything?
This is a real leap, but starting from where the non-inverting output is a Darlington pair, and there seems to be another one on the inverting output. So do they make a differential?
So I think you are right. So we can see here this part, where effectively the non-inverting input and the inverting input of the overall amplifier is that circuit. Well, it's not as simple as the one I'd shown you here, but that's a differential amplifier. BJT, the two BJTs here. Resembles a lot. Okay, it's not exactly the same, but it is that. It's a differential amplifier in input. In input. Anything else? The rest is a bit more complicated, but there is. Let's see who can find the Darlington pair. There is one that is bam, you know, it shouts at you. Yes, here it is. Clear as Darlington pair. This kind of things we didn't mention. Obviously, it's not possible to mention everything. These are called current mirrors. Okay. If you are curious enough, go to, there is one reference that it's kind of very good, and I think the level is good as well, is the reference I call reference 24, which is a nice book. It's only an e-book available online, and there you can find you know, many of these things that probably we haven't covered, like the current mirrors. Q7, let me see, where is it? Q7 and Q5. Yes, this is, it looks like, it looks like the feedback pair. No, sorry, no. Let me bring it up. The feedback pair was, no, it is different, you see? Is that what you wanted to say, the feedback pair? In the feedback pair, you need the emitter or the collector connected to the base of the other, while there, the emitter or the collector connected to the base, while here you have, well, you have the emitter of this one connected to the base here. My problem is that the base of this one is connected to the collector of the other. It's a different configuration. I've seen it, and unfortunately I don't remember how it's called. I've seen it somewhere. Never mind. So that was just to show you what amazing things you've done up until now, and what they allow you to, you know, the doors that they open. Okay, so the operational amplifier that maybe it looked like a black box really up until now, maybe is not such a black box anymore. That's my hope. Okay, so I wanted to conclude. We have really few minutes. I wanted to show you. I had prepared at the very last of this part of this lecture. I had some like applications, circuit applications. Mainly, what I wanted to show you is the amplifiers we went through, mainly some that we solved during the lecture, either last week or the week before, which was the voltage divider, for example, and calculating the numbers, also in terms of AC analysis, what would be the amplification and so on and so forth. And then use, I was planning to come here actually, to be honest with you, with the instrumentation to demonstrate that this amplifier gives exactly what you would expect. Unfortunately, then I realized I was coming here, A and B tier 1, so thanks to timetabling, I had to decide that that's not possible because I knew that it would have been a nightmare. And so, but I will do this through a simulation tool that it's also an opportunity to tell you that it exists. It's free, you can download it, and you can play with it if you want to, anytime, and you know, whatever you do in the future, to be honest, it's something that I think if you like this field, it can always turn out to be useful. So very briefly, just because we don't have much time, so this was the CD voltage CE3 voltage divider amplifier with RE bypassed. We solved, this was the circuit we actually solved 2 weeks ago. There was an example. I had it also in my notes, and these were the conditions we used, the assumptions, and so on and so forth. IC had to be 2 milliamps. We had set some conditions on VCE. We solved it, and we found out that the values of R1, R2, RE, and RC had to be this one here. So R1 5.27, and so on and so forth. So if we now take this design and we use the formulas that we calculated from the AC analysis that we did last week for this specific configuration, we can calculate the 4 famous parameters, input impedance, voltage amplification, and so on. And so for this specific application, the input impedance would be, if you do the calculation with the values on top, would be this much, 600 ohm, which is not a lot. The IAV infinite, which is this quantity, I'm guessing obviously on HIE and HFE, I'm assuming HFE is 100, HIE is 1 kilo ohm, RC is the value that comes, is this value here, comes from the DC analysis. So we would expect 188 amplification with a minus in front. Similarly, AI0, we would expect minus 61, and Z output 1.88 kilo ohm because it's the same as RC. So, do you believe it? Shall we check it? Let's check it. So, I have really few minutes to do this. Let's check it. So with RE bypassed. So this is the circuit. It's exactly, you see, I've put R1, R2, RC, and RE are according to the design we've made. I've chosen the input signal to be 1 millivolt. Okay, just I don't want something big. And just so the circuit can run, I've put R load very big, like 1 mega ohm. So let me run the simulation. This will run now in AC. Let me run it first in DC so that we can check that IC is correct. I will post these little programs on Canvas, so you have it if you want to play with it. I will tell you also where to get the program. The program is LTspice. It's free, downloadable, and comes ready with all the models, everything. So it's really cool. So I'm doing the AC analysis now, DC analysis. So the numbers shown here indicate the currents and the voltages, the DC voltage. So let's keep just an eye on IC. IC is 0.0019, whatever. So it's nearly 2 milliamps. According to the design, we wanted it to be 2 milliamps. Another thing is, for example, to check, what else to check? Well, we have to do it on the fly. VC minus VE, you see VC is 11.4, VE is 3.6. If you do the difference, is roughly, it should be, according to the design, 7.5 volts, this difference. It's roughly there. This was VCE, the difference between VC and the VE. So anyway, the DC design works. We can, another thing, nice thing to check is that the current in R2 and in R1 is roughly 2 milliamps. This was according to the design. And so effectively the current through these two resistors is roughly 2 milliamps, very much bigger than IB. If you check here, IB is 1 × 10⁻⁵, much, much smaller. And this was the whole point of the voltage divider, if you remember. Set a current flowing in this voltage divider that is much bigger than IB, so that I don't need to know the beta of the transistor. The transistor will draw the current it needs from the voltage divider, okay, without affecting it, because the current flowing there is huge. So anyway, this is just to say the voltage divider, sorry, the DC analysis was done properly. Let's now run the AC analysis. So I've run it in frequency from 100 Hertz to 1 megahertz, which is the low frequency regime, as we called it. And I will plot here now. First thing we want to check is the voltage amplification, for example. So I will plot V out over V in, as is defined on the diagram. So let me put it, it's in dB, let me put it in absolute, in just plain values. So we predicted 180. This is giving 140. It's okay, it's quite close, I'm happy with it. The reason I'm happy is that I didn't know the specific value of HIE and HFE for this specific BJT. I'm using here a generic BJT, okay? I'm happy. Also note the phase. The phase is this dashed. The phase is minus 180. This means this accounts for the minus in the voltage amplification. There is a pi phase shift. So that's fine. We checked the first parameter. Let's check. I'm wondering if there is a lecture now. I think there is. Let me check. Oh, if you noticed, I've checked the voltage amplification with RL very large. This means when RL is very large, eventually infinite, what we are calculating effectively is AV infinite. If I wanted now to calculate what we called AI0, which is the amplification in current when the terminals output are shorted, I need to set this to 0. RL must be 0. So now I will run the simulation again, and I will now plot the current amplification. So we check that one as well. I will plot, which is for the output. I can take IC. Where is IC? IRC. No, sorry, not IRC. IC out. ICO I can use. It's on the output branch, that's fine. ICO over IC in. We were expecting, according to our 61, minus 61, and we get 53, which is quite good as well. We didn't know exactly, I remember the parameters. So, and again, 180 degrees is the phase shift. So again, this accounts for the minus. So, last thing to check, I wanted to check the output impedance. How do I check the output impedance if I have a simulation tool like that? Remember, the output impedance should be 1.88 kilo ohm. So one thing, this is one clever thing I could do. If I'm already suspecting that the output impedance should be 1.88 kilo ohm, I could set R load to 1.88 kilo ohm and check that the voltage amplification becomes half. How do you like this idea? Because of the voltage divider, isn't it? So I will remove this from here, delete. we will plot, well, let me run the simulation first with the new load resistor. If for now I get a voltage amplification that previously with an infinite load, AV infinite was 140. If now becomes 70, it means that indeed 1.88 kilo ohm is roughly the output impedance. So we do again V out over V in. Ta-da! Around 70. So this means indeed our analysis was correct. Okay? So this is a nice way. I suggest if you are interested in the field to download this software and play with it. You know, it's quite easy and handy. You can, you know, check how things works. So thank you for, this was the last lecture. Thank you for following these lectures up to this point. Next week we have one tutorial on Tuesday, 2 hours, and one tutorial on Friday. And then one more tutorial will be 1 hour only after Easter. Okay, so I'll see you next Tuesday for the tutorial. We will do the quizzes from the last lecture and the lecture before. Oh, obviously, because today was, let's say, chat between people that are curious, there is no quiz today, okay? Because this is not part of the exam, at least for this academic year, okay? So I'll see you next time.